All right, make sure I'm recording. Good deal. All right, so this really is an extension of the previous section, right? We talked about arithmetic operations on functions there, and the notion was that you wanted to build new functions from existing ones. And the same sort of thing is going to happen here, only now we're going to introduce a new way of doing that. And that way is called composition. So if I give you two functions, f and g, we say the composition of f and g, and I'm going to denote that as f circle g. That's defined by taking g of x, so the function g of x, and using it as an input into the function f of x. So we write f of g of x. So g of x is the expression going into the box that you use if you're using box notation to write the formula for f. All right, and so let's just look at an example, probably the easiest way. It's not hard, the notation is new and potentially confusing at the beginning. So I give you two functions, f of x is 2x minus 1 and g is 5x squared plus 1, and I want to compute the composition of f circle g and g circle f. So different order here, right? And we'll make a note at that at the end. So first, f circle g of x is f of g of x. And what does that mean? Well, whatever's in the parentheses, I'm putting in for the input into f. And so what I'm putting in the parentheses is the formula for g of x, which is 5x squared plus 1. But f of that is just 2 times 5x squared plus 1 minus 1. Right? So I'm literally plugging that in for my x in the formula for f. And then once you have that, you can simplify it like you normally would. Distribute the 2 through and then some add like terms. Same way here, if I want g circle f of x, that is g of f of x, but I want to then plug in the expression used for f of x here in for x. And so I'm going to plug it in, I'll get 5 times 2x minus 1 squared plus 1. And then if I were to simplify this, I need to FOIL this out, as I did here, and then distribute that 5 through and then combine. Okay? All right, and so notice here that there's no x value that makes any of these undefined. So the domain is both all real numbers, but in particular, notice that f circle g and g circle f are not the same. And so the order in which you compose two functions actually can and most often does matter. So you have to be careful. All right, so let's go to example 2. Oops. All right, so example 2, we have f of x equals 3 minus x squared and g of x equals radical x. And I want f circle g, right? So here, f circle g of x is f of g of x. I'm going to plug in the expression for g of x in for the input for f. So I'm going to plug in the radical x for the x here. That's my 3 minus radical x squared. Now to simplify that, you square the square root to get 3 minus x. All right, so easy enough. That's the simplification of the composition f circle g. But we have to find the domain, and here you have to be really careful. If you just look at the very end, you'll say, that function's linear, the domain's all reals. True, but that's not true all the way through. Right here, you used g of x to get at this function, and at the beginning, g of x was only defined as long as x was non-negative. Right? G is a square root of x, and you can't take the square root of a negative number. And so you have to factor that in to how you compute the domain. Right? So not only is the end result important, what goes in here, the x's that you're allowed to put into the inner function constitute the domain as well. And so the domain of f circle g here is really this half open interval, or half closed interval from 0 to infinity. All right, so go ahead and try this your turn. Right, for each pair of functions, I want you to compute f circle g and g circle f and state the domains in each case. All right, go ahead and try that and see what you get. Okay, so for the first one, f circle g, I'm going to plug in g of x for the input in f, right? So that's what I'm doing here. and then distribute your 2 and simplify to get that end answer. And then similarly, G circle F is G of f of x. I'm plugging in f of x in for the x in my formula for G. That's what I've done here. And then square this by foiling and then simplify to get this end response. All right. Notice in both cases, there's never an x for which it's undefined, and so the domain of both these is all reals. All right, the next one, you have a rational expression and a linear one. If I want f circle G, that's f of G of x. I'm plugging in G of x in for the x here. And so I plug in x plus 2 for my x, and then simplify to get that guy. All right. G circle f of x is I'm going to plug in f of x as whole fraction in for x in the formula for G. And so what I get by doing that is that guy plus 2. And then if you add those two, you have to get an LCD, right? Because you're adding 2 fractions technically. That LCD is just x minus 1. So you apply that to the second term here, and then add across to get this simplified expression. All right, and so now, and then lastly, we have f of x is radical x minus 1, and g of x is x plus 5. And so f of g of x, I'm plugging in the g of x here, right? So I have now the square root of x plus 4, right? And so notice we need x plus 4 to be non-negative. And so in the end, the domain is everything to the right of, including minus 4. G of f of x is the next guy. So if I plug in f of x here for x, I get the square root of x minus 1, and then 5 added to that. And that's what I have here. The domain is everything for which this guy is non-negative, and so the domain is everything to the right of, and including 1. All right, just as before, these are in fact the same functions that we had from the example in the previous section. You can be given graphs to define a function rather than expressions, but you can still use the information from those graphs each time to compute compositions at particular values. And so let's look at f of g of 0. So to compute this, we need g of 0. G of 0 is 1. And then f of 1 is a half, right? So it's the y value at that point, which is a half. And so f of g of 0 is 1/2, right? You always work your way from the inside outward with these. G of 0 is 1, then the outer function at that value is a half. All right, so the next question is, does 2 belong to the domain of f of g of x? Well, let's see. Let's see if the computation when I plug in 2 makes sense at both stages. First off, g of 2 is perfectly defined. G of 2 is 0, right? So it hasn't broken down there. But now if I plug in 0 as the input into f, notice I only ever have an open hole, never a closed point on that y-axis, which is x equal to 0. And so f of 2 does not exist, right? And so the answer is no, 2 does not belong to the domain of f of g of x, because had it been in the domain, you would have gotten a value out. All right. And then finally, g of f of minus 2, f of minus 2 is 1, g of 1 is 1, and so you get 1. G of 1, yeah, I'm sorry, is a half. Sorry, right there. So it's the y value at that point. So you get a half. Okay, so go ahead and do your turn 2. Basically, it's the same question, same exact reasoning that applies. Try that, stop the video for a moment, and then check yourself when you are finished. Okay. So notice it's asking, is 3 in the domain of f circle g of x? And how about the other one? And for the first one, it is, because f circle g of 3 is f of g of 3, but g of 3 is 2, and f of 2 is 0, right? So that first one is perfectly well defined. However, if you reverse the order, g circle f of 3 means g of f of 3, but f of 3 doesn't define because there's only ever an open circle on 3. And so G circle f of 3 is not defined. Okay, and then G of f of 2 is 0, G of 0 is 1, and so G of f of 2 is 1. Okay. All right, go ahead and try this. So it's the same sort of thing. I will talk about a couple of these toward the end, but basically you're doing the same exact thing we just did with the two functions that you used in the your terms in the previous section. So give these a shot and see how it goes. All right. So take a look. None of these have any domain issues attached to them, so it wasn't too bad, right? So if you have any issues with those, let me know during our conversation on Zoom, and then we can talk about them, of course, at that point. All right, so now in calculus, it'll be often important for us to go backwards from a more complicated function to compositions of easier ones. So we're going to want to break complicated ones down into pieces at various stages in Calc 1. And so what I want to do here is look at x plus 5 to the fourth, for instance. What I want to identify are two simpler functions that when I compose them, I get x plus 5 to the fourth back. All right, and so for instance here, the overall structure of m of x equals x plus 5 to the fourth is something being raised to the fourth power. And so one of my functions, the outer function, the last thing I'm going to do is raise the inner guy to the fourth power, right? So my f of x, I'm going to use just x to the fourth. Raise whatever the input is to the fourth. The inner guy is the thing being raised to the fourth, and that's just x plus 5. And so if I define g of x to be x plus 5, notice that with those two functions, f of g of x is equal to f of x plus 5. But if I put in x plus 5 for x here, I indeed get m of x back. Right? So you're trying to identify the overall structure of a function and then see what's inside of that function as the input, and then that should give an indication in terms of what the composition or the decomposition ought to be. All right, so let's go ahead and try your turn 4. Same idea. Some of these look more complicated, but the principle is the same. You want to identify two functions, the overall structure, and the inner thing is what you're putting into the variable in that structure to get this function, and see what you got. All right, so let's look at these. For the first one, m of the outer function, the basic structure of the function is something, the square root of something. And so my outer function f will be the square root of x. What am I taking the square root of? Well, that would be that 2 minus 3x squared. And so if I compose these two simpler functions, f of g of x, I get this back. Right? For part 2, what I have here, structurally, I have a rational function, right? I take 2 minus something and 4 minus that same something to get this function. So if I define f of x to be this guy, then g of x, the thing I'm plugging in for x, is x squared, right? And that composition would work. There are other ways to go around this one, but this is probably the most direct, I would say. All right, this guy here, notice I'm using I have the 5 minus 2x occurring in two different places. So that's an indication that I probably want to replace it by just an x to get the outer structural function, right? So overall, this function m of x is something cubed minus 3 times that same something squared plus 1. And so what that tells you is the outer function is f of x equals x cubed minus 3x squared plus 1. And then the inner function, what am I cubing and what am I squaring? Well, that's the 5 minus 2x in this case. Okay. And then finally here, this function is really 1 minus the absolute value of something. And so the outer function is 1 minus the absolute value of x. And then what am I taking the absolute value of? Well, that's that 3x squared plus x. Okay. So that's how you want to think about decomposing more complicated functions into a composition of two simpler ones. All right. Here, this is kind of late in the game. This is kind of related to the notion of computing that difference quotient again. So I won't go through this again, just read this on your own. But we've seen this sort of calculation when computing f of x plus h minus f of x over h. And we're about to see an example of that again, albeit in a more complicated setting. But if you have issues with this computation, make sure you review this part of the manual and do this your turn. All right, so let's look at this example, example 6. We've seen this sort of expression before, albeit only for quadratics, right? But we want to look at it now for more general functions. And here we're going to consider a very simple rational function, just 1 over x. And what I want to do is compute this expression using this function. Okay? And so first, I need f of x plus h. So think again as of f of x using that box notation. F of x equals 1 over x is the same as f of box equals 1 over that box. And so f of x plus h is really just the expression 1 over x plus h. Okay? Notice that plus h is with the x down below. This is not the same as 1 over x and then plus an h on the outside, right? The entire x plus h is in the bottom. Okay, so having that in hand, I can now substitute directly in the pieces I have for this expression. All right, so I have 1 over x plus h, that's the first part, minus f of x over h. All right, that's the entire fraction. And what I have to do is simplify this, right? And so this is a complex fraction of the sort that you reviewed in the first chapter. Right, so I'm going to leave it in this form, though you could write this as parentheses around the top and then a division sign h, right? That's perfectly valid to do as well. Just deal with the division by h very last, right? Don't piddle with that h now, leave it alone, no matter which of these approaches that you use. All right, so what I have to do in the top to simplify is get an LCD. And so I need to multiply the top and bottom of this guy by x and the top and bottom of this guy by x plus h. That's what I do here. The common denominator is x times x plus h. Again, do not multiply out the denominator, right? Leave it like that. The top is x minus x plus h, right? So what you want to do here to further simplify the top, distribute that minus sign through, right? And then cancel the x's. Right, and so what you have left is just a minus h over that guy and that whole fraction over h. All right. Now, this is where you have to be careful with how you deal with fractions. You have a fraction divided by c, right? The fraction is that guy divided by h, that's your c. Well, that means a over b divided by c. But remember, when you divide fractions, that's equivalent to multiplying the initial fraction by the reciprocal of the one after the division sign. And so I'm going to rewrite that as a product of a over bc. Okay? What does that effectively do? It moves this h that was down below into the denominator of the fraction up top. That's what I've done here. Okay? Once you've done that, the top h and that bottom h now cancel. Okay? And what that then gives you is that expression. All right, so this one trips up a lot of people initially, not only at this stage, but the entire simplification stage, and then of course rewriting this complex fraction as a single fraction. So make sure you go through this calculation more than once, just to make sure each step makes sense, and then you'll have worse ones to work with going forward. All right, I'm not going to do this one with you. This is just a quadratic. You've done that in couple sections ago with quadratics. So I'll leave it up here. You can look at that just to make sure that you have that. All right, and the last thing is how to view symmetry about the y-axis and the origin using composition notation, right? And so I've mentioned this in the past, but I want to kind of mention it here. Remember, our function is symmetric about the y-axis, or it's even if you go the same distance on either side of the y-axis with your inputs, but then you get the same output. So in other words, if I go x or negative x for my input, the y values are the same, but the y values at those particular x's are f of x and f of negative x. So if this statement is true for every x in the domain of f, the function's even. This graph will be symmetric about the y-axis. If this is true, if you go the same distance on either side of the origin and the y's are opposite signed, then it's called odd, right? This negative multiple out here means it's opposite signed. All right. So go ahead here, look at this example. We want to check to see if these functions are even or odd. So let's look at the first one. What you want to do is use those two expressions I just gave you as tests, right? So I'm going to see, let's compute f of negative x, and let's see if it equals f of x. If it does, the function's even, right? Let's see. So we plug the negative x in for x here, and I get just this expression. But remember, you can take the absolute value of a product that's equal to the product of the absolute values. And so this negative multiple does nothing, right? It just goes away. And so what in the end you get is absolute value of x plus 3, but that is f of x, right? And so what you've shown here is that f of negative x equals f of x, but that means the function's even, right? The minute it's even, it cannot be odd, right? You can't have a function be both even and odd, all right? And so the graph of this function actually looks like the absolute value of x, but then shifted up 3 units. Remember those translation results. If you do that same thing here, all right, let's see what happens. G of minus x is equal to this guy, but I can, if I simplify that, negative x cubed is just negative 1 times x cubed. I could yank the negative out, right? But that's not equal to g of x, right? G of x is without the negative sign. So what that tells you is that g of minus x does not equal g of x, and so g is not even. However, it is odd because if I multiply this by negative 1, that negative goes away and I do get g of x, right? And so negative g of negative x does equal g of x, and so the function is odd. And if you graph it, in fact, what you'll get is something that looks like this. All right. And then this one, I let you read through part 3. You do the same thing. You plug in negative x everywhere there's an x and see if that equals either h of x or negative h of x. In this case, it's neither, right? You can check that out. A function need not be either even nor odd, right? It doesn't have to be either one. And so in this case, you don't get these expressions being equal, and that's perfectly fine. All right. Your turn 7, which I'm just listing here, gives you more practice. So you can go ahead, stop the video and try them and then check yourself. But it's the same idea, right? You want to use those two composition tests for even and odd to see what the symmetry is. All right. Okay, so we've reached the end here. Try these homework problems. Again, they're mostly standard. Just be careful with the computations, right? Especially with, let's say, number 12, part 4 in particular, right? Be careful with that. So give those a go and see what happens and let me know. All right, take it easy.